Hi all, welcome to my brief tutorial on designing CPA formulations with the predicted equivalent ice avoidance capabilities. So the idea here is you might have some popular CPA formulation BS55 that you know is going to avoid ice in your system, but maybe it's not good in terms of the biological outcome. Maybe the functional recovery is not there, so you want to use a different CPA formulation, but then the question is what different one to use. Uh, you'd want something that also avoids ice. Maybe you'd want to do like a fair comparison of CPA toxicity screening, where you compare the CPA formulations at sort of uh, the same predicted ice avoidance capability, so the same CPA concentration. How do you do that? Well, you would use a process like this. So this is the spreadsheet I've developed to do this. Yeah, somewhat unimportant, but here are some keys here. The red highlight is just above the predicted toxicity limit. Um, and yeah, the gray highlight is maybe to ignore these formulations. The highlights aren't too important, but just yeah, getting into the process of how to design a new CPA formulation is what I wanted to focus on in this video. So this CPA formulation, it's composed of different components. It's composed of DMSO, dimethyl sulfoxide, symbolized as D. It's composed of ethylene glycol, symbolized as E, propylene glycol, symbolized as P, and formamide, symbolized as F. No ethylene glycol in VS55, though there is in other popular CPA formulations such as VEG. And then the total concentration is, the sum of all three of these, so that's why this is a sum function here. And to have, to have more ice avoidance capability, you increase this. If you make it be 65 weight by volume percent, if you make this be 30 instead of 24, something like that, then that weight by volume percent will increase, and you'll have more ice avoidance capability. But on the flip side of that, you're exposing the cell to more CPA concentration, more of a drug. It's probably going to cause some sort of bad outcome, and so hence why we might want to, you know, have this be not too high but high enough to avoid ice, uh, and uh, and so that's like one way to think about it is like we want to design CPA formulations of similar weight by volume percent, but it's not a super precise way to think about it because these different CPAs confer different ice avoidance capabilities at the same CPA concentration. So 25 weight by volume percent of DMSO is not the same as 24 weight by volume percent of PG, and so on. How do they differ? Well, they differ according to certain parameter values. I've put some in here. Here are the parameter values, with the parameter being beta as defined in the Vice publication, and these values being simple unit conversions from the data published in that. I think it's a 2010 paper. Uh, and yeah, these are just used to get a sense to just inform a process that's more precise, that's better than just controlling for the same weight by volume percent, because uh, as is the case, propylene glycol is the best per unit weight by volume percent at avoiding ice, and formamide is the worst per unit weight by volume percent at avoiding ice, with DMSO and EG in the middle here. Uh, and so how to account for that? Well, we can use the following process to account for that. So instead of having this be 55 everywhere, we use this constraint equation instead. This constraint equation is takes into account these parameter values, these beta values, as well as whatever the CPA concentrations are. And the idea is to have this number be exactly the same in each new CPA formulation you design, if you want to design it to be like a fair comparison to VS55 in a biological study, or just in general if you want it to be, a certain value. And so, let's say you're coming up with a new solution, um, so like I'll just go through the process. I came up with this one, this DEP formulation. So here, um, you know, if I get rid of this term here, this gets zeroed out because these cells are set equal to this. So if you want each CPA in your composition to have the same weight by volume percent, you can just, set this cell equal to the cell here, and then, whatever you input here is going to be the same, and so on. And so you can see if I input 10 for a total weight by volume percent of 30, then this number is going to be too low. So it's going to be poorer at avoiding ice than VS55. We want this number to be equal to 1314. So, you can change this to 20. Okay, we're getting closer to 1314, but now we're overshooting it. Maybe if this is 15, you can get closer. And you can keep going like that to arrive at a good formulation. A better process is to just use something like Solver. So this is a plugin, so you can search how to install Solver on Excel, but this process I like better. So you can set this objective cell, so whatever your objective cell is, in this case, it's this constraint equation cell. So this one is the objective cell to a value of 1314, because that's what we're trying to get. And here's the cell to change. We change this cell. This is a G5 cell. And in turn, of course, the G4 and G3 cells will also change because they're set equal to the G5 cell. So that's when we're going to change. And so what this solver is going to do is it's going to iterate through values of G5 so that this objective is equal to this constraint. So it's doing that sort of process I was doing manually before, but this is going to be faster and get something very precise. So I'm going to click solve here. And you can see that it changed these values. It has a ridiculous degree of precision here, kind of unnecessary. But at any rate, that's the way I prefer to do it, is to use Solver, but you can just do it manually here. And just some quick checks to make sure this makes sense. Like, okay, I was saying that formamide is the worst in terms of avoiding ice per unit weight by volume percent. Does this make sense? I think, sure it makes sense, because we're kind of replacing formamide for EG here. EG is better at avoiding ice, so we need less total CPA concentration to get the same ice avoidance capability. So yeah, that's the idea. That's the process. That's how I've ended up, coming up with, all sorts of different solutions here. I'm not going to go through this. And, if you don't want it to be equivalent to VS55, you want it to be equivalent to something else, maybe, I went through that process as well, of course. Yeah, this sheet just shows some comparison. Yeah, I think there's just some information as to how, I got certain toxicity limits. Don't take this too seriously. And then, just a summary on the parameter values as determined from that Weiss 2010 paper. With PG being the best at vitrifying, the best at avoiding ice, and so on. So that's all the information I have. You're welcome to contact me for this spreadsheet if you want. And this is something I found helpful in my work, and hopefully someone else will too.